All right, everyone. Welcome back after lunch. I'm here to talk about structured streaming in Apache Spark. And my name is Tathagat Das, or more easily TD. That's what everyone calls me for obvious reasons. And to start with a little bit about me, who I am, I started the Spark Streaming project. For those who are familiar with Spark and Spark Streaming, it came out of AmpLab, and so I was a grad student there. But right now, it's been 6 years since then, and right now I'm focused on building structured streaming, which is what this talk is all about. And I'm a member of the Apache Spark PMC, and currently a software engineer in Databricks. For those who are not familiar with what Databricks is, it's basically a company built by the original team that built Spark in UC Berkeley. That includes me. And our mission, we started this company with the sole mission that we want to make big data simple for everyone. And so to do that, we have built this product, which is essentially our unified analytics platform, built on top of Apache Spark in the cloud. And it is a single platform where you can do all sorts of data science, data engineering, any kind of big data analytics, streaming, machine learning, anything you can think of on our platform. Anyways, I'm not here to talk about Databricks. I'm here to talk about streaming. So one thing that is, I think a lot of people understand, whoever has tried to build a real streaming application, is that building robust stream processing applications is hard. And let's understand, let's clarify why it is actually hard. So there are essentially three main reasons. One is that dealing with stream processing, you have to deal with a lot of complex data. There's a lot of different diverse formats. You have JSON, Avro, custom binary, all sorts of data can come in all sorts of formats. And data can be dirty. You can have corrupted data, you can have late data, you can have out of order data, and you have to deal with all of these in your streaming applications. Which means that the workloads that you run on the streaming platform can be quite complex. For example, because of the out of order data, you have to, whenever you're doing analytics on the data streams, you have to consider what is the time in the data itself, not the time when the data arrived, because it can be out of order. So this is called event time processing, where you take the time in the data, the event time. And you may need to combine these streaming workloads with other kind of workloads like stream processing with interactive queries. The data you're getting out of stream, you may want to query it interactively. You may want to do machine learning on the streaming data while learning or serving. All sorts of combination of stuff can be required to be built for your streaming application. And more importantly, your streaming application has to interact with a very large variety of complex ecosystem of storage systems. So there can be SQL databases, NoSQL databases, file systems, Parquet, different file formats like Parquet, ORC, all sorts of combination of stuff. And in general, this is a distributed system environment, so we can have system failures, and you have to also deal with those kind of failures, thus making the overall system that you have to build pretty complex, yet something that you can reason about, something you can give you guarantees that your answer will be always right despite any internal failures. Now, to make all of this simple, we actually built structured streaming. And at a high level, it is essentially a stream processing engine built on the Apache Spark SQL engine. So that makes it by nature fast, scalable, and fault tolerant. It provides rich, unified, high-level APIs, just like all of Apache Spark, to deal with all these complex data and complex workloads, combining them all together. And you know, the Apache Spark has a very rich ecosystem of data sources that allows you to interact with complex storage systems that are present in this ecosystem. So when we built structured streaming, we essentially started from the drawing board with the knowledge of what are all the things that were the old Spark streaming that I built, the D streams, for those who have used that, where all the things were insufficient. We learned by working with hundreds of customers and thousands of developers in the open source community. We learned from those mistakes, from the shortcomings, and we went back to the drawing board and we designed structured streaming from scratch. And the key idea we realized while we were on the drawing board is that you as a developer really should not have to think about streaming. Because thinking about streaming as a separate manner is naturally hard, and frankly, we feel unnecessary. What you want to do, really rather do, is that you want to simply write simple queries, which is essentially the semantics of the results that you want. So you should write just the simple queries. And it should be Spark's job to automatically figure out how to run that query and continuously update the answer, the result, when data comes in, new data comes in into the stream. So you should not have to worry about any of that. You should be able to just write simple queries like SQL and that kind of simple stuff. So that led us to the simple idea that why not treat all streams as unbounded tables. So basically, imagine the stream where there are new events coming into the stream. You can imagine that as a table where new rows are getting added all the time. So this table is essentially continuously appended, and it is essentially unbounded. Now this is a completely conceptual table, and I'm showing you how you can think your streaming applications in a different way that ultimately makes things easier to write your streaming application. So now that if you think of your conceptual table as your stream as a conceptual table, if you sample that table at a certain interval, let's call it the trigger interval, let's say every second, you will see that this table is essentially growing continuously as new data comes in. So this is essentially the conceptual model we are going with, and I'll explain in this presentation how this conceptual model makes things far simpler than what most of us are used to. So this input table is continuously growing. Now let's say you apply some sort of query on top of it. Could be anything. I'll go into the details later. But what in the end comes out is a result. And this is true for any batch or streaming or anything. You have an input table, you have a query, you get a result table. But in the case of this streaming conceptual model, this result table is continuously changing as the input table is getting new data. So now as the result table is changing, what we want to do ultimately is push all the changes out into an external storage system. For example, you're doing some sort of ETL, you want to see the new clean rows put out into an external system. That's essentially the output, defined as output, that whenever the result table changes, how to push the output, the changes as output to an external storage system. So here we can define multiple different output modes, which define exactly what set of changes to push out. For example, let's say your query and the result table is such that pretty much the whole table is changing every time there is new data. Let's say you have some sort of statistics and your whole table all the counts in the table has to change. So for example, in that case, you can write the entire result table, the complete result table, using the complete output mode. Alternatively, let's say you only want the new data that has been added to the table, not any of the changes. And in some workloads, you never change the old data. You only add new rows. So there is append output mode for exactly that purpose, where only the new rows will get added to the external storage. And there can be update mode as well, where only the updated rows in the result table will get written out to an external storage. Okay, so now it's important to note that this is just a conceptual model. The full input doesn't need to be stored or materialized by Spark to actually compute the result. What Spark essentially does is that it takes the query that you have written and converts it to a purely incremental query, which knows how to update the result by computing only on the new rows that has arrived since it was last updated. So, this incremental, converting your simple query to an incremental query is what is taken care of by Spark, and you don't have to worry about it at all. But the final goal of this conceptual model is that this allows both streaming data as well as batch data to be represented using a single API, which is Apache Spark's Dataset and DataFrame. So basically all of these static or streaming data is a table, and tables are one and the same and represented as a dataset DataFrame in Apache Spark. Can I see a show of hands of how many people here know about datasets and DataFrames in Apache Spark? Okay, pretty much quite a large majority, but still not everyone. So just to bring everyone on the same page, a dataset DataFrame is essentially a collection of objects, a distributed collection of objects with a known schema. So you know that what do the objects have? Do they have how many columns there are? What are the type of the columns in each row? So this collection knows about that. So essentially, it is conceptually equivalent to a table. So now you can create data frames out of file system data, database, Redshift, MySQL, JDBC, Parquet file formats, ORC file formats. You can create data frames from a whole set of different storage systems, and it is a completely growing set of stuff. Now, you can either operate on that data by calling simple SQL-like operations like group by, sum, count, and all of that. Aggregations, I'm not going into details of how deep the API is, but it's very deep. I'm going to just give a glimpse of it. But I want to highlight the fact that you can either write DataFrame queries in the form of simple SQL-like operations, but which is and this API is essentially great for data science stuff, who are data scientists who are familiar with Python pandas and R DataFrames. Or you can write in absolutely pure SQL, which is great for business analytics, BI focused guys who do not who are more comfortable with SQL and GiveQL and stuff. And that also generates data frames underneath, and you can interoperate between SQL and data frames. Or if you want to get more hands-on and you want compile time safety, which often people building data engineering pipelines, data engineers often want that, you can basically convert it to full data sets, which essentially gives you full compile time safety. So you can do all sorts of operations while ensuring type checks at compile time. The cool thing is that across all of these, you're still using the same data frame and APIs underneath and the same SQL is underneath. So no matter what nail you choose, whatever hammer you choose to hit your nail, you get the same performance benefits, same performance guarantee across all this different APIs. Anyways, so to give you an example of how data frames look like, so if to write a simple batch query that reads from a JSON file, selects some columns and writes it out to a Parquet file, this is what the query would look like. So you essentially have something that defines the input, something that defines the query and the final result, and the result.write at the third code snippet essentially says how do you want to write out the result to an external system, in this case a Parquet at a destination path. To convert this to a streaming query, it's absolutely simple. Your input will change a little bit because instead of reading it once, you want it to continuously read the stream. So in this case, you just convert read to read stream, and what it'll do is that instead of reading the JSON file once, it will essentially read all the JSON files continuously added to a directory. So that's a JSON file stream. And your query stays exactly the same because it's all data frames and the same data frame operations, but the output again changes slightly. So you, instead of just writing it once, you want it to write a stream of outputs as Parquet, and instead of just running it once, you want to say that start running it and keep running it continuously in the background. So these are the only few things that it needs to change. But the key idea is that your actual query operations do not need to change at all. And when you call start, what the system underneath does is it takes this code that you've written, it converts it to a logical plan, which is a purely logical representation of what is it that you want to do. Is it that you want to select something, you want to select some columns, you want to filter out some rows, etc. Then it does all sorts of optimizations on top of it using Spark's Catalyst optimizer. finally, it generates an optimized physical plan where all the super crazy optimizations we have done in the last 3-4 years in our Spark SQL engine, you get all the collective benefit of all those runtime and logical and runtime optimizations for free in this, and you get an optimized physical plan, which is essentially an incremental plan. And then the engine automatically keeps running this incremental plan repeatedly whenever new data comes into the system. So Spark SQL does essentially all the hard work of converting your simple batch-like query into a series of incremental plans running on streaming data. And you don't have to think about how this happens at all. The other thing you don't have to think about is any sort of fault tolerance, because the system takes care of keeping precisely which offsets of data, which is, for example, if you consider Kafka, which range of offsets have been processed each time there is an incremental execution. It takes care of saving that into an external write-ahead log, so that in case of any kind of failure, it can recover exactly where it left off, thus giving end-to-end exactly one's guarantees without you having to worry about what happens if things go wrong. Anyway, so for those, a neat tidbit here is that for those who have actually tried D-streams and worked with Spark streaming before, the checkpointing here is fundamentally different from how it used to work over there, because there were limitations in D-streams where you could not recover from your checkpoint if you changed your code and things like that. We have avoided, we have learned from those mistakes, and we have avoided all those complications. Here we save only the offset, so even if you change your code within certain constraints, for example, adding a filter to filter out corrupted data and stuff, you can always recover from the offsets that has been saved as part of the checkpoints. This simplifies things a lot. So this was a high-level overview of what structured streaming is. Let me dig a little bit deeper to actually walk through a simple yet kind of complex use case, which is streaming ETL. So traditionally, ETL has been done in the way where you have a stream of data coming in. Typically, they dump the stream of data directly into some sort of files without any sort of processing to kind of persist it as soon as possible. That is done within seconds. And then there is a periodic job every hour at best, and every day, every 6 hours, 12 hours. But in the order of hours, the file dumps are taken, processed, and converted to a more structured form like a table. So this is essentially how ETL has been traditionally done. But the problem with this approach is that this is not sufficient for time-sensitive, latency-sensitive operations. Because, for example, if you want to do intrusion detections on your streaming data, or anomaly detection on streaming data, it's not worth waiting hours before you can do anything with the data and see whether there was an anomaly in the last day or not. You've lost the ability to react to the data. So one of the goals, one of the main motivating use cases of structured streaming was to actually make this simpler by avoiding all this two-hop thing and making streaming data available in a structured table-like form as soon as possible within seconds. Let's walk through a concrete example. Let's say you have JSON data being received through Kafka. You have to parse the data because the JSON is heavily nested. You want to parse it out and kind of maybe potentially clean it up, but at the basic level, parse it out, flatten it, and do basic processing, and then store the parsed data as a structured Parquet table, so that you can do other operations like interactive operations, etc., on that Parquet table as soon as possible. And you obviously want end-to-end fault tolerance guarantees. How much code do you think you would have to write? That's it. For doing all of these together, this is all the data you need, all the code you need to write for doing this query. Let me actually walk through each of these steps. Step 1, you need to define your input, which in this case is Kafka. So you have to define how to read by specifying your Kafka Bootstrap servers as options in this in this form. You can specify what you want to read, basically subscribe to a topic or a pattern of topics or a specific topic partitions, etc. And you can specify where to read from, either from the latest data or from the earliest data or a specific topic offset. All of these essentially can be specified through these options. Of course, you're specifying the format as Kafka. And what this load essentially does, it essentially returns a data frame. This data frame essentially has these few columns where you have the key and the value as binary data. The topic it was read from, the partition it came from, the offset, timestamp, when it was received, etc. So now that you have this data frame, you can do all sorts of transformations on top of it. For example, the first step I need to do is that convert it to string, because ultimately it's JSON, so it's UTF-8 or something encoded string. So you want to convert the binary data to string, which is what this first line does. You're casting the binary value to a string and naming it JSON. Then, now that it's a string, I want to parse it as a JSON. And for that, there's a very handy inbuilt function called fromJSON, where you specify which column to read to parse and what is the schema of the JSON. And what the system will do is automatically convert the string into a bunch of nested columns. And this is what this select call returns the data frame essentially of this format. It's a bunch of nested columns. And then ultimately you want to flatten it out, because flattening it out makes it more efficient to store stuff in Parquet and things like that. So again, flattening is pretty simple. Just say data.star, it converts these nested columns into just flattened out columns. And that's it, that's your final result. And so the cool thing that you should remember here is that, so Spark SQL comes with a large number of built-in APIs to perform complex data transformations like this, like from converting back and forth in JSON, exploding all sorts of SQL functions, time functions, string functions, mathematical functions. The list is on. So you should take a look at our blog post. We have written a bunch of blog posts to kind of highlight all these cool things that Spark SQL has internally, which goes above and beyond what is present in our programming guide. You should I highly recommend you take a look at our blog posts. So now that the final result table is ready, I want to essentially write it out. So here I'm specifying what is the output format, which is Parquet. And I incidentally know that later, when I'm going to interactively query the Parquet table, I'm going to most likely query it in terms of last 6 hours of data, or last 12 hours of data, or even last 5 minutes of data. So based on that, I want to partition the data, because every time I query, I don't want to read the whole Parquet table. So I want to partition the data by hour or date. In this case, I've chosen to partition by date, in which case it will say that what it will do is that every data from different days will get written in different subfolders. Usual Parquet partitioning, you guys know about that. So, and then finally, I want obviously fault tolerance. All I need to do is specify this checkpoint location into HDFS compatible file system, and that's it. The system will take care of everything else, doing all the checkpointing and stuff. And then finally, obviously, call start. And when the start is called, it actually starts a query that is continuously running in the background on the associated Spark cluster. And what I get back is this handle, this query handle, which can be used to both manage as well as monitor the query. So for managing, I mean, you can stop the query, you can stop the query, you can ask for its health, you can monitor its progress in terms of what is the input rate, what is the processing rate. All of those can be, those metrics can be acquired from this query handle. And furthermore, in a single Spark cluster, you can have any number of queries running and sharing the same resources, therefore giving much better resource efficiency. And so as this query runs, essentially data from Kafka will be converted to Parquet table within seconds. And so your interactive, complex, ad hoc analytics, batch queries, etc., can start using that data, running complex queries on the data within seconds. The other cool thing to remember here is that the way we update the Parquet table, it ensures something called prefix integrity. What prefix integrity, without going into too much details, what it means is that whenever the Parquet table is updated, you will either see all the updates together, or you see none of it at all. So the updates are essentially added to the Parquet table atomically, thereby ensuring that whenever you're querying the data, you are not going, you're getting consistent results, as opposed to seeing inconsistently updated Parquet tables. Again, more information on our blog. In Spark 2.2, which is about to come out in hopefully a week, it's in the release candidate 4. There's probably going to be a release candidate 5, usual Apache process. But so within maybe a week or so, Spark 2.2 will be out. But in that, we have added a lot of additional Kafka support, including writing directly out to Kafka, where it's the same. You can specify the topic to output, and it will just convert it into binaries and write it out. And you can also run direct batch queries and interactive queries directly on Kafka. So you don't even, so you can imagine Kafka as a purely as a storage system like GageDFS, and topics are essentially like files. So you can specify that read this topic from this offset to that offset, and it will run a single batch query or interactive query directly on Kafka. And this is something that makes Kafka also a lot more powerful as a long-term storage platform. Anyways, we also have support for Amazon Kinesis as part of our Databricks runtime environment, and Databricks runtime is essentially our own packaging format that includes Apache Spark that is available on our platform. And similar to Kafka, you can read from Kinesis by specifying where to read, what is the name of the stream to read, where to start reading from, latest or earliest, and stuff like that. So this was relatively a simple query, where you're just essentially parsing and filtering. You're not really doing any sort of aggregation. So whenever you want to generate statistics, you definitely have to do some sort of aggregation. And in a lot of use cases, you have to actually aggregate considering the event time of the data. So let's talk about how we work with event time in this in structured streaming. So typically things like how many events did I get in the last 1 hour, or that were generated at the source in the last 1 hour. So those sort of windowed aggregates and stuff, this is what I'm talking about. And here the old DStream APIs were insufficient because it didn't give you the right APIs to kind of express your event time windows. It only allowed you to express windows on when the data was received by the system, not the original data. So in this new model, what we have done to address all of these different late data, out of order data, event time challenges is that we have considered windowing as simple as a grouping. So essentially, if you think of it conceptually, windowing essentially is a bunch of buckets. Let's say if you have 1 hour windows, you have essentially 1 hour buckets, and every event that comes in based on the time step in the event, you should be able to put it in the right bucket. So it is essentially some kind of grouping. And so in the API as well, we have essentially done exactly that you can specify windows just by saying group by window of 1 hour using this column in the data as timestamp. And note that this is a column in the data, that is you have already parsed the data. You may convert the timestamp into the right timestamp, like UTC, all sorts of data, date format, etc., cleanup, modification, etc. And after that, you can just simply say, here is the timestamp column which has the cleaned up timestamp. You are windowing by 1 hour. I'm just saying 1 hour as tumbling windows, but you can also say 1 hour every 10 minutes and things like that. And that's it. So what this gives essentially the number of records every hour. You can also group by at a per device, by other columns. For example, you want the same aggregates, for example, average signal strength of each device over the last 10 minutes. This is window, timestamp 10 minutes, as well as grouping by the device. Finally, the average of the signal strength. So your windowing becomes as simple as grouping. And of course, this supports your user-defined aggregate functions. There are different APIs for specifying your aggregate functions and stuff. And when this actually runs, the system actually takes care of all the stateful processing that needs to be done. So, by the way, this is stateful because as data comes in, you need to essentially update the averages and the counts and any sort of aggregate. So you need to remember what was the previous average whatever the previous intermediate aggregates were, which is essentially state. So, and this is distributed through the entire Spark cluster, so this is distributed state, and the Spark takes care of actually making sure that the previous state, every time there's a trigger and there's new data to be processed, it picks up the right version of the previous state and generates a new version of the next state. And the state is essentially stored in memory, but it is backed into something like HDFS S3 using write-ahead logs. In all, you don't have to worry about how this state is managed. This is completely opaque to you because Spark takes care of ensuring exactly one's fault tolerance guarantees for the state as well. You don't need to worry about any of these. What this also does automatically is automatically handles late data, where even if a data comes in late and out of order, it will figure out which is the right bucket to put in, and the state is that bucket is stored as a state already. And whenever there is late data, it can always, this is the latest window every time, but whenever there is late data, it can always put it in the old windows, old buckets. And so it automatically takes care of maintaining the right aggregates and right counts even the data is late. But one thing to notice here is that as the system is adding more and more windows, the system doesn't know really when it can remove old state. Basically, it doesn't know when the state is not needed anymore. For example, if I'm doing 1 hour windows, I really don't care much about the windows 7 days ago because that that state is never going to be updated, but the system doesn't know that. So the system cannot really forget any of the old state, and the state will keep growing. To prevent that from happening, what we have added is something called watermarking. Watermark is essentially a moving threshold that specifies how late the data is expected to be. For example, if I expect my data to be at max 10 minutes late, then I can say that I can specify in the system that watermark to move 10 minutes behind the newest event time seen by the system. For example, if at this point of time, if the event time, that is the max event time seen by the system is 12:30, then I'm telling the system that data can be at max late. So the oldest data that may arrive from now on is 12:20, with the threshold, the threshold being 10 minutes. So what means that the system can automatically figure out that windows that are older than 10 minutes, it doesn't need anymore, and it can clear off all that state. So essentially all data, any data that is newer than the watermark may be late, but it's still allowed to aggregate. If the data just happens to be older than the watermark at any point of time, or let's say it came later than 10 minutes, the system will have already cleared of its state, so it will drop the old data and clear out the state. And so with this, you can essentially control how much you can control the trade-off between how much state to keep and how much late data to consider. So if you have an application that requires 1 hour of late data to be considered, then you have to allow the system to have more in-memory state, and vice versa. So it's a trade-off that you can control. So these, and this watermark is something that you specify simply by saying with watermark on the timestamp column and how late is it allowed to be. And this operation is completely a no-op, ignored for if the same query is run in batch mode, because in batch it really doesn't make sense, but the query would still work exactly as if this statement wasn't there. So you can write this query, and if you run this query on batch mode, watermark is ignored. If you run this in streaming mode, watermark is used to clear off all state. And this is also useful only in streaming operations. Other operations will just plainly ignore it. So this is like a purely processing time optimization that you can add if you want to control the amount of state the system has to maintain. And underneath, the engine will take care of actually figuring out, based on the timestamp in the data, this is the event time, this is the processing time. Based on the timestamp in the data, what are what is the maximum event time the system has seen at any point of time. Based on that, it will continuously update what the watermark is, and based on that, any future events, if it's late but newer than the watermark, will get considered. Any events that are older than the watermark will get dropped, and its corresponding state will also get dropped. Again, I've written a blog post about this that explains in more details. Even the programming guide also goes into more details about this. Please take a look. Anyway, so this is, I'm running out of time, so I'm not going to talk in a lot more, much more about about other stateful stuff, but just to give a sneak peek on what is the new thing that is coming in Spark 2.2 is essentially arbitrary stateful operations using map groups with state. For those who have worked with these streams, this is exactly similar to update state by key and map with state, if you have used those. But, well, I'm saying similar, but this is actually a superset of what you can do using map with state. So, but what this essentially is, for those who are not familiar, is that you can essentially maintain arbitrary user-defined state and continuously update it. So in the previous example, I was talking about aggregates, and that was completely happening behind the scenes. You were just specifying that I want average, and the system takes care of maintaining whatever intermediate state is needed. In this case, you can specify exactly what needs to be maintained as a state. And this is useful for things like sessionization. For example, to take example from our own use cases, we essentially maintain Spark clusters in the cloud on Amazon AWS. So for our own monitoring purposes, what we need to do is essentially monitor a Spark cluster's health by maintaining a session of what this cluster is doing. And whenever there is new jobs and new events that is occurring on the cluster, we continuously update the current state of the Spark cluster. And then we can, and looking at the state, we can do things like, oh, there were 5 errors in the last 1 hour, or 5 errors in quick succession, something may be wrong, do something about it. So that kind of session level logic you can write using this. Currently, Scala and Java is supported. We would add Python support in future. The other thing that is built-in supported are timeouts. So basically, if you were, to continue with the example, if my Spark cluster hasn't given me any new events, any new health heartbeats in the last 1 hour, then something is probably wrong, and you want to take action on it. So we have inbuilt timeouts as part of this operation. You can specify that 1 hour in terms of either event time or wall clock time. You can do that. There are other operations. I'm going to gloss over it. Please take a look at the slides and my previous talks when it comes out. Streaming deduplication. We have stream batch joins. We have stream joins. We don't have stream joins yet, but we are working on stream joins very soon. And we have used all of these to build our own complex application of essentially what I said, monitoring our own Spark clusters, building dashboards on top of it, all using our own platform as sort of a dog fooding model. We have built alerting systems on top of it, all using structured streaming on our platform. And also you can do ad hoc analysis. All of that has been built. And I'm not going to go into details of this pipeline that we have built, but the key thing to remember is that this is a complex pipeline. Each step of here has different latency requirements, and we process a very large number of records very efficiently. Again, the details is in my Spark Summit talk. And the key thing to remember is that Spark structured streaming is now not experimental anymore. It is generally available in Spark 2.2. We have processed over 3 trillion rows in the last month in production. And we have more structured streaming customers than dstream customers at this point. Anyways, more details in our blogs. And please try Apache Spark 2.2 on Databricks. It is, you can get a free account, and you can try this for free on databricks.com. Thank you very much. Do we have time for questions? One question. Okay. Yes, so you can You can do pattern. So the question was, do we have to convert to a schema to do pattern matching kind of stuff? You have the flexibility to do any kind of stuff. You can read the data just as binary blobs from Kafka and do pattern matching directly on the bits, or you could convert it to some sort of parsed format and then apply the same kind of pattern matching on smaller parts of the data. You have the full same level of flexibility with RDDs, with DataFrames as you had with RDDs. Thank you very much.